All right, guys, so we've talked about indicators and used them previously, but we're going to talk a little bit about what indicators actually are and how to know how to pick the appropriate indicator, because this is something that you'll deal with in your lab tomorrow. So we can use indicators to signal the equivalence point of a titration. So we know whenever we see a color change in the indicator, if we are using the appropriate indicator, we should have reached that equivalence point. And indicators are dyes that change color at different pH ranges. And remember, we said whenever the indicator reaches its end point, the end point is the pH where the indicator should change color. And if we pick the right indicator, the pH of the end point should correspond with the pH at the equivalence point of the added volume when we reach neutralization. So we're going to have to make sure to select an indicator with an endpoint approximately equal to the pH of the equivalence point in a reaction. If we pick the wrong indicator, it will change color even though we have not reached that equivalence point where moles of acid equals moles of base. So remember, there are different indicators, and this indicator chart shows you their color change that occurs and approximately what pH that color change occurs. So like we've used phenolphthalein previously, which is down towards the bottom, and notice that it changes from like colorless to red a little higher than a pH of 8. If our target pH was closer to 6, we would want to find something that changed color around 6. So we might use like the alizarin or the bromothymol blue. There are also indicators that work well for the diprotic acids, and they have two different color changes. So like if you look at the alizarin right here that I mentioned, there's one color change that changes around a pH of 6, but then there's another color change around a pH of 11. So that may be appropriate for some of our diprotic acids. And that's where we can see the two different equivalence points for those. With acid-base indicators, they are typically a weak acid or a weak base. And these have different color forms whenever they are ionized versus non-ionized. So here, like our acid form of our weak acid is red, and then whenever it is ionized and in that conjugate base form, it is blue. So whatever we have more of is kind of the color that we see at that point in time. And this can kind of go back to Le Chatelier's a little bit from equilibrium. So if we were to increase the number of hydrogen ions on the product side, that would shift the reaction towards the reactant side. So equilibrium would shift towards the left. And since we have more of the acid form, we would see more of the color of the acid form, which would be red. So that would be that color change that we see, is it would change from blue to red because we're shifting towards that side of the reaction. Whereas if we added hydroxide, now hydroxide is not in this equation itself, but hydroxide reacts with hydrogen. So that would decrease the amount of hydrogen, shifting the reaction towards the product side. So it would shift towards the right. And on the right, we have that ionized conjugate base, which would be blue. So that would cause the reaction to shift to blue from red. And that color change, which is the endpoint, occurs whenever the molarity of the acid form is equal to the molarity of the base form, which, if you remember, when acid and base are equal, that should be equal to our equivalence point as well, if we picked the right indicator. And whenever the molarity of the acid form of the indicator equals the molarity of the base form of the indicator, the pH of the solution should equal the pKa of the indicator. So whenever we are picking the appropriate indicator, we are going to have to be looking at the pH at that equivalence point, and is it similar to the pKa of the indicator? So looking at why indicators change color at different pH ranges, it's because every weak acid or weak base has its own Ka or Kb value. And since they're unique, pKa is going to be equal to a different pH value. So that's why they have a differing pH range. So the pH range of when that color change occurs is dependent on the indicator's acid strength. So some of the weak acids, their color change is going to occur at those higher pH values. So how we're going to select an appropriate indicator for the given titration is we have to select an indicator with an endpoint approximately equal to the pH of the equivalence point in the acid-base reaction. And remember, we said for that, the endpoint, we are going to find pKa of our indicator. And we want pKa to be close to that target pH. It may not be exact, but it should be within 1 is our goal. So the end, excuse me, I can't go back, can I? All right, it won't let me go back. Belay said the end point should be within 1 pH unit of the equivalence point. So if our equivalence point pH is 7, we would need an indicator that would change somewhere between 6 and 8 would be our goal. The closer to 7, the better. But as long as it is within 1 pH value, that pKa value, it would be appropriate. Looking at why some indicators have 2 endpoints. And like I said, these typically are going to be diprotic weak acids because there are 2 hydrogens that ionize. There are 2 different color changes that occur because there are 2 different Ka values for the original weak acid and its non-protonated form, its ionized form. So that's why we see some of those different ones. Where you guys will have to do this, so you guys need to look at your pre-lab for tomorrow's lab, because like I said, you have to know which indicator to use before we actually set up our titration. If you look at the pre-lab, it's questions 1 and 2 are the ones that we are focusing on right now. And I apologize, it won't let me pull it up on the iPad at the same time. So the first question has you figure out the pH of the equivalence point when acetic acid is titrated with sodium hydroxide. Once you find that pH range, you need to look at the chart that is below number 1. It has 5 different indicators and it has their pKa value showing you what color change occurs. Whatever pH you find for 1A, which indicator has the closest pKa value? And that's going to tell you which indicator you need to use for that first titration that we're doing tomorrow. The second titration we're doing tomorrow is going to be dealing with the weak base ammonia being titrated with hydrochloric acid. And it does the same thing. It has you find the pH at the equivalence point and then refer back to that indicator chart to pick the appropriate indicator that has the closest pKa value to our target pH. For the pre-lab question number 3, this one you're not doing any math with. It is talking about if we had a weak acid with a weak base, which we don't typically do. But it wants to know, should the pH at the equivalence point be at 7, less than 7, or greater than 7? And to think about this, it does give you the Ka and Kb value for the two substances. Which one is stronger? That should give you a clue to, is it going to be a lower pH if the acid is stronger, or a higher pH if the base is stronger? So that should help you fill out the pre-lab. And then I would go ahead and start setting up a data table for tomorrow. It does have you input our target equivalence point, which should be calculated from your pre-lab, and which indicator we're using. And I would leave yourself some space. Do not try to cramp them in together. And then whenever we come in tomorrow, we should be able to set up our titrations and get them going. That way, because we need to do both titrations completely tomorrow during class, because it is graphing them using the probes for us. And we cannot necessarily leave the probes set up overnight to continue collecting on Friday. So utilize today, get your pre-lab done, make sure you know which indicators you're looking at, and I will see you tomorrow.